Welcome to my microwave class. Hi, in this video we will focus on the double stub matching technique. Let's take a look at the present figure. A lossless transmission line of characteristic admittance YC is ended by a load YR, creating a reflection coefficient whose magnitude is assumed to be different from unity or zero. If the magnitude of the reflection coefficient is equal to unity, then the problem is hopeless. That is, it will never be possible to match that load to the circuit. If the reflection coefficient is equal to zero, then it's already matched and there is nothing else to do. We aim to make some transformation to this circuit so that its input impedance matches that of the transmission line in order to avoid reflections. Therefore, the matching network will convert the load admittance YR to YC. The double stub matching technique comprises the use of two short-circuited secondary lines called stubs of unknown lengths S1 and S2 located at S equal D1 and S equal D1 plus D2 respectively. Thanks to this configuration, we aim to convert the terminal load YR located at S equal 0 to a matched load YC located at S equal D1 plus D2. It's worth mentioning that when using the double stub matching technique, the lengths D1 and D2 are assumed to be fixed according to some technical aspects. The design of the matching network comprises finding the lengths S1 and S2, which can be found either analytically or thanks to the use of the Smith chart. Unlike the simple stub matching technique, we show it is not always possible to achieve matching. That is, S1 and S2 do not exist in some circumstances that will be defined later. To illustrate the use of the double stub matching technique, we will consider in this video a terminal impedance ZR equal 100 plus J50 ohm, a characteristic impedance ZC equal 50 ohm, and line length to be 6 of the wavelength for D1 and 2/3 of the wavelength for D2. Let's go the analytical way first. Because the stubs are connected in parallel, it is more convenient to work with admittances rather than impedances. So we compute the terminal admittance YR. So we invert ZR to find YR. We also compute the value of the characteristic admittance. So we invert ZC to find YC. Also, in order to avoid the manipulation of constants, it is common to work with normalized or reduced admittances. They will be noted using lowercase symbols in this video. For example, the reduced load admittance will be equal to lowercase YR, which is easily calculated as follows. The reduced YR equals the plain YR divided by YC, which is equal in this example to 0.4 plus J 0.2. The reduced admittance YR has a reduced conductance GR equal to 0.4 and a reduced susceptance BR equal to 0.2. Let YM1 be the input impedance of the first transmission line before the stub junction. It can be found using the following formula, which can be expressed in a normalized form as follows. To ease formula manipulation, we set U1 equal tangent beta D1. Note that U1 can be calculated because D1 is known. We find U1 equals 1.732. Let's compute now the value of the input admittance. We find YM1 equal 0.698 plus J 0.779. The input admittance YM1 has a conductance GM1 equal 0.698 and a susceptance BM1 equal 0.779. Let YP1 be the admittance of the first transmission line after the connection of the first stub. If the input admittance of the first stub is YCC1, then we can write YP1, which is Y at S equal D1 plus, equal Y at S equal D1 minus, plus the admittance of the stub YCC1. Thus, yp1 equals ym1 plus ycc1. From the transmission line theory, we know that the input impedance of a short-circuited stub is purely imaginary. It is related to the line length S1 as follows. Ycc1 equals minus g over tangent beta S1. Thus, the stub brings a susceptance B1 equal minus 1 over tangent beta S1 to the input admittance. Thus, we get Yp1 equals to Ym1 plus Ycc1, which is equal to the conductance Gm1 plus J multiplied by Bm1 plus B1. Note that B1 is unknown because the length S1 of the stub is to be determined. Finding B1 is equivalent to finding S1. The admittance Yp1 can be moved toward the generator. Because of the length D2 of the second transmission line, Yp1 will be transformed to an admittance Ym2. Here again, after connecting in parallel the second stub at S equal D1 plus D2, the new input admittance will become Yp2 so that Yp2 equals Ym2 plus JB2, where B2 is the susceptance brought by the second short-circuited stub. At that point, we would like to have an input impedance matched to the transmission line, that is, Yp2 equals Yc. The corresponding normalized expression is lowercase yp2 equals 1. For this to occur, the admittance at S equal D1 plus D2, noted Ym2, must satisfy the following relation. Ym2 equals Yp2 minus JB2, which is equal to 1 minus GB2. Of course, B2 is to be determined in order to find S2. We will use the following expression. B2 equals minus 1 divided by tangent beta S2. Knowing the expression of Ym2, it is possible to find a new expression of Yp1 by moving the latter by a distance D2 toward the load. Replacing the expression of Ym2 yields the new expression of Yp1, where U2 equals tangent beta D2, which is equal to 1.732. Let's separate the real and imaginary part of Yp1 by using the conjugate technique. We find, after some algebraic manipulations, the new expression of Yp1. Recall now the first expression of Yp1. From these two expressions of Yp1, we can extract a set of two equations by equalizing the real and imaginary part. The first equation of this set will allow us to find the unknown B2. Afterward, B1 will be determined thanks to the second equation. Here is the expression of B2 that we find after some manipulations. If the quantity under the root is negative, then B2 doesn't exist, and the double stub matching technique is not usable. However, if the quantity under the root is positive, two solutions B21 and B22 are possible. In our case, we get a quantity which is positive, leading to two solutions, B21 equal 1.532 and B22 equal minus 0.377. As tangent beta S2 equal minus 1 over B2, we end up with S21 equal minus 0.093 lambda and S22 equal 0.193 lambda. Because S21 is negative, we add half a wavelength corresponding to the periodicity on a transmission line. Thus, the retained solutions are S21 equals 0.408 lambda and S22 equals 0.193 lambda. Knowing the susceptance of the second stub, it's now possible to find the susceptance of the first stub. Recalling the second equation of the set, we get the expression of B1. For each solution B21 and B22, we evaluate the corresponding solution B11 and B12. We find in this example B11 equal 0.565 and B12 equal minus 0.867. Finally, we can get the possible length of the first stub. S11 equals 0.319 lambda and S12 equals 0.136 lambda. Note that the accepted solution pairs are S11, S21 or S12, S22. It's not possible to mix them, that is, we cannot use S11 with S22 or S21 with S12. Now let's solve the problem using the Smith chart. First, when using the Smith chart, we always work with normalized values. So the normalized ZR equal the plane ZR divided by ZC, and we find 2 plus J. Once again, we prefer to work with admittances rather than impedances, so let's get the value of YR using the chart. Recalling that the value of the admittance is the mirror of the impedance regarding to the center of the chart, we proceed as follows. First, we locate the point representing ZR on the chart. Then we draw the circle of constant reflection coefficient. We draw also a straight line comprising the center and ZR. And finally, we get YR from the intersection of the line with the reflection coefficient circle. Although it is unnecessary to evaluate YR, we get it from the chart for the sake of comparison with the analytical method. We get YR equals 0.4 plus J 0.2. The next step consists of evaluating Ym1 by moving YR by d1 over lambda equals 0.167 toward the generator. For this purpose, we pick up the starting point on the toward generator scale and we find S over lambda equals 0.463. Then we walk toward the generator by a distance of d1 over lambda equals 0.167. So we arrive at the position S over lambda equals 0.463 plus 0.167 equals 0.630. But because the position is greater than a half, it is necessary to subtract 0.5 to the result. Therefore, we get S over lambda equals 0.630, which is equivalent to 0.130. Let's draw a straight line from the origin to that position. The value of Ym1 is obtained by finding the intersection of the line with the constant reflection coefficient circle. We find Ym1 equals 0.70 plus J 0.78. At this stage, we are tempted to evaluate Yp1 as follows. Yp1 equal Ym1 plus Ycc1, which is equal to 0.70 plus J multiplied by 0.78 plus B1. But it's rather impossible because the admittance of the first stub Ycc1 is unknown. However, we know that Ycc1 is purely imaginary. Thus, Ym1 and Yp1 have the same real part, while the imaginary part is different. This means that Ym1 and Yp1 lie to the same R circle on the Smith chart. In our example, it is the R equals 0.7 circle. Any point of this circle represents a potential Yp1 solution. Finding the right Yp1 and knowing Ym1 will allow us to find the susceptance B1 of the first stub. Let's now move to the end of the transmission line at S equals D1 plus D2, where we expect an input impedance Yp2 equals to Yc in order to accomplish the impedance matching. That is, Yp2 equals Yc. In normalized form, we get Yp2 equals to 1. Here again, we are tempted to evaluate Ym2 using the following formulas. We know that Yp2 equals Ym2 plus Jb2. That is, Ym2 equals Yp2 minus Jb2. But as Yp2 equals to 1, then Ym2 equals to 1 minus Jb2. But it's not possible since the susceptance of the second stub B2 is unknown. However, we know at least the real part of ym2. Thus, we know that ym2 lies in the R equal unity. Any point of this circle may be the desired solution. Let's move toward the load in the counterclockwise direction, all the potential solutions ym2. This action defines a new set of potential solutions yp1. To proceed, we must rotate all the points lying in the unity circle by a distance of d2 over lambda equals 0.667. This is easily achieved by rotating the center of the R equal unity circle, then redraw the entire circle. For instance, the original circle center is located at S over lambda equals 0.25 on the toward load scale. We must walk a distance of d2 over lambda equals 0.667 on that scale to reach S over lambda equals 0.25 plus 0.667, which is equal to 0.917, which is equivalent to S over lambda equal 0.417 on the Smith chart. We draw a line from the origin to that position, then we identify the center, and finally we draw the circle. Now we have two circles containing both of them the potential candidates for yp1. The first circle was obtained from equations at S equal d1, whereas the second circle was obtained from equations at S equal d1 plus d2. As the solutions must belong to the two circles, we choose the intersections. We end up with two solutions, yp11 equals 0.7 plus 1.25j, and yp12 equals 0.7 minus 0.08j. Knowing the value of yp1 helps to find the susceptance b1 of the first stub. Indeed, yp1 equals ym1 plus ycc1, which is equal to ym1 plus jb1. So jb1 is the difference between the two admittances. jb1 equal yp1 minus ym1, which leads to b11 equals 1.25 minus 0.78 equal to 0.47, and b12 equals minus 0.08 minus 0.78, which is equal to minus 0.86. Now we must find the value of the second stub susceptance. For this purpose, we first find the value of ym2 simply by moving back the retained value of yp1 toward the generator. We know in advance that the values of ym2 must belong to the R equal unity circle. Starting from the locations of yp1 on the toward generator scale, we walk for distance of d2 over lambda equals 0.667 in the clockwise direction. We stops at S over lambda equals 0.473 plus 0.667 equals 1.140, which is equivalent to 0.140 on the Smith chart. For the second point, we have S over lambda equals 0.157 plus 0.667, which equals 0.824, equivalent to 0.324 on Smith chart. We then draw straight lines from those locations to the origin of the chart. The ym2 points are the intersection of the lines with the R equal unity circle. We find ym21 equals 1 minus 1.5j and ym22 equals 1 plus 0.38j. These values allow us to find the susceptance of the second step. Recalling that ym2 equals 1 minus jb2, we obtain b21 equal 1.5 and b22 equals minus 0.38. Now that the susceptance of the stubs have been found, it's time to find their corresponding length using the Smith chart. Let's take a blank chart and locate all these susceptance. Note that they are all on the R equals 0 circle. As we are building the stubs from short circuit, we also locate the short circuit admittance on the chart. Now, we draw lines from those admittances to the center of the Smith chart. Then, using the two-word generator scale, we locate all the previous admittances on that scale. Finally, we find the length of the stubs by measuring the distance between the susceptance and the short circuit. Here are the results. Let's do a comparison between analytical and graphical results. We summarize the obtained results in a table and we compute the relative error when using the Smith chart. The average relative error is about 0.51%, which is very good for a graphical method. This ends our video, hoping you have enjoyed it. See you soon in other videos. Bye.